In part 1 about structures, we looked at how to declare and initialize an assembly language structure. Here in part 2, let's see how to store and retrieve data to and from structure variables. As you might guess, storing data into a structure variable isn't quite as easy as it is with a high-level language. But it's not horrible either. Here's a simple example. I'm using the pet structure from the part 1 video, and I'm declaring a variable named pet1 of that type. Since our pattern has no default values, pet1 contains all junk. I'm also declaring a character array to copy a name into the name1 field. I'm going to use the string primitive instructions to put the name into the structure variable. So I set up my destination pointer, but I'm not pointing the destination register at the pet1 variable. Instead, I'm pointing it to the name1 field inside that variable. And to do that, I'm making use of the dot operator, which says, go to this field. Then I set up the source pointer. And finally, the ECX register as a counter that's going to let me move single bytes repeatedly. Next, I try to do something similar with the wait field, but I run into a problem. I can't use the move instruction to store a floating point immediate value, so we've got to do a workaround. I declare a temporary real4 variable and place the value I want to store into it. Then I use a move instruction to copy that variable into the EAX register. Now you might be thinking, hey, why is it letting you copy a floating point number into an integer register? And my answer is, the EAX register is 32 bits and my floating point number is 32 bits. The EAX register doesn't know that the bits in my temporary variable are supposed to be interpreted as floating point. The register just sees 32 bits and goes, oh, I can handle that. That's why in the part 1 video, I chose the real4 data type. It's 32 bits big. Now that I've got the 42.7 value into the EAX register, I can copy that into the wait field, and the assembler is going to be happy again. The only thing left to do is to copy an age into the age field, and for that I use just a simple move instruction. So let's watch this happen in Visual Studio. Let's begin at the top. In my pet structure definition, I'm making the name1 field have a default value of all x's. That's just for illustration purposes here, but it can also help you when you're debugging your programs. You can see in the memory1 window all the x's in RAM. Now these 4 0 bytes represent the real4 wait field, and these 4 bytes are the double word age field. I've also added the pet1 variable to the watch window down at the bottom. Let's look at that watch window a little more closely. If I click the little arrow by the pet1 variable, it opens up and shows me the 3 fields of the structure. Now that's pretty neat. We could compare the watch 1 window with the memory 1 window and get a pretty good idea of what's going on. Let's start stepping through the code. The first thing I want to do is to get the address of the name1 field in my pet1 variable. On line 21, I store that address into my destination EDI register. I want to do something similar with the temporary string that holds the name I want to store. So on line 22, I move the string's address into my source register ESI. I want the ECX register to hold the length of my temporary string, and that's got to include the 0 at the end. So on line 23, that's what I do. Then, on line 24, I use a repeat prefix to copy all the bytes from my temporary string to the name1 field of the variable. You can see that change easily in the memory 1 window because I've got it displaying individual bytes. So this part shows the ASCII codes in hex, while this part shows those codes translated to text. And make sure you see that the 0 was copied also to mark the end of the string in the name1 field. In the watch window, the name1 field only displays the first letter of the pet's name because the assembler knows that name1 is an array of chars, so it just displays the first one being pointed to by the array name. The wait field is still 0, and so is the age field. Now I need to move my temporary wait variable into the EAX register. That occurs on line 26. If you look up in the register window, the EAX register contains an odd-looking number. How could that be 42.7? You have to remember that's actually a real 4 number. What you're seeing in the EAX register then is how those real 4 bits are interpreted as an integer. That's okay, as long as we know that's actually a floating point number when the bits are interpreted correctly. Think about that. Now we need to store that weight into the PET1 variable, so on line 27, that's what happens. Check out the Memory 1 window. The value in red is the number that's in EAX, but now it's in Little Endian format, so all the bytes are reversed. Unless you're some sort of savant, those hex digits won't mean anything to you. I know they don't to me, but here's where the Watch 1 window comes in handy. We can clearly see that the weight field contains the 42.7 that it should. Then I store 6 years into this PET age field, and again you can see the change clearly in both the Watch 1 window and the Memory 1 window. We'll come back in just a little bit to Visual Studio for another example. Now don't get me wrong, I like this textbook, but one thing I think it fails to do sometimes is to show you how some of this assembly language works inside a procedure. For instance, a lot of the code assumes you're working in main all the time, when in reality you're probably going to be inside a procedure. So let's take our last example and see what it would look like if I had to store data into the PET1 variable but using a procedure. All my data remains the same, but now I need to set up my parameters. So first I'll push the address of my PET1 variable. Then I'll push the address of the temporary string holding the name that I want to store into the PET1 variable's name1 field. Then I'll push the temporary variable that holds the weight that I'm going to store. And finally, I'll push the length of the string that I want to store so that inside the procedure I can set up the ECX register. Now this is important. Everything my procedure needs is being sent to it as some sort of parameter, with one exception, and that's the age I want to store. If you understand what I'm doing here, it'd be a pretty simple matter to have another variable that holds the age you want to store and push it as a parameter also. So you can see the procedure call right here on this last line. Let's look inside the procedure itself. So here's my procedure, and on the first line I make sure I use the uses directive so that I can restore my registers at the end of the procedure. Then come the parameters. In the red box is the order that I push the parameters. But in the procedure itself, they have to be in reverse order, which means the length of the string I want to copy into my variable is the first parameter on the stack because it got pushed last. Next is the parameter I'm calling weight, which is actually a copy of the temporary weight variable back in main. The next parameter is a pointer, and it points to the name I want to copy into the variable. Then finally, I've got the pointer to my actual PET1 variable. So much for parameters. Now let's start actually using that data. The parameter named PET_pointer is actually an address, so I just copy it directly into the EBX register. To set up the EDI register, I have to tell the assembler that I want the name1 field of the thing that EBX is pointing to. This is not just a simple variable. Instead, it's a pointer to a structure, and that structure has 3 fields. I have to let the assembler know which field EBX is pointing to, and here's how I do it. Pay particular attention to the form I have to use to accomplish that. The parentheses have to be there to override the order of operations that would occur if I just use the dot operator by itself. If your program's not working right, here's the first place to look. Setting up the ESI register is easier because a parameter named sourceString is already an address. Setting up the ECX counter is easy because I sent the count parameter to this procedure. Notice again that the procedure doesn't have to reference anything outside of itself. Once I've gotten the counter set up, I use the string primitive instruction with the repeat prefix so that I can copy the desired name, again including the 0, into the name1 field of my PET1 variable. Just as I did before, I have to copy the 32-bit weight value into the EAX register and then copy that into the weight field of the variable. And once more, here's that special syntax that I have to use. Then we get to the age field, and like I said before, I should have sent that as another parameter. I just didn't think about it. It'd be a pretty simple matter to fix that, though. In fact, y'all will probably get the chance to do that very thing.
Yay!
At the end of this procedure, I put the return instruction. The number after it is 16 because I had 4 32-bit parameters. Yeah, a little more complex than before, but a lot more useful and a lot more real world. Here's what it looks like in Visual Studio. Similar to our first version of storing data into the pet1 variable, I've got my memory1 window pointing at the pet1 data. I've got the watch1 window pointing to pet1, and I've got the 3 fields of that variable showing in the watch window. So I'm all set up to step through the code. The first parameter will be the address of my pet1 variable. I push it on the stack. Next comes the address of the string I want to store in the name1 field. It goes on the stack, followed by our real 4 weight, which takes up 4 bytes on the stack. And last, I'll push the number of characters in my temporary name string, including the 0. That's what I'm going to use to set up the ECX register inside the procedure. At that point, I can transfer control to the store data procedure. At the start of the procedure, I indicate which registers I'm going to use so that they can be restored later. As explained earlier, I'm naming the parameter count for the number of characters in my string to copy, weight for the real 4 weight amount, source string is the name I want to copy into the name1 field, and pet pointer is the address of my pet1 variable. On line 36, I'm copying the address in pet pointer to a general purpose register. Here I picked EBX. You can see the EBX register change, and notice in the memory1 window it points to the start of my pet1 variable. Then I set up my destination register, EDI. The syntax says go to the pet structure that EBX points to, and then point to the name1 field of that structure. Since we sent the address of the pet1 variable as a parameter, EBX is really pointing here. As described earlier, setting up my source register ESI is simple. So is setting up the ECX register. Once again, the procedure refers only to its parameters to do its job. I use a repeat prefix to copy the string into the name1 field. And you can see the pet1 variable change in the memory1 window and in the watch1 window. I use the EAX register to copy the weight into the weight field. Notice the change in the memory1 and watch1 windows. Store the age, and the effect of that code is reflected also. The only thing left to do then is to clear up the stack and return. 4 double word parameters equals 16 bytes to clear the stack. The next idea is to look at storing data into individual structures in an array of structures. Before we get into talking about arrays of structures in assembly language, let's make sure we understand that concept in high-level language. So we'll go back to the high-level structure definition from part 1 of our look at structures. That definition is up here in the corner. In C++, I could declare an array of pet structures like this, and that array would look like this in RAM. Each one of the structures would have its own name1 field, its own weight field, and its own age field. I could refer to those structures individually as mypets0, or mypets1, or mypets2. The numbers inside the brackets, the 0, the 1, or the 2, are called indexes. Said a different way, those are the slot numbers occupied by the individual structures. That shouldn't be new to you because that's how all arrays work. Now suppose I want to store some data into the third structure in the array. In C++, it's simple. I use the name of the array, followed by the index in brackets, followed by the dot operator and the member name. So to store Beethoven as the name for the third structure, I would use this code. That's going to change the name1 field right here. Then for the weight, I would do something very similar, and that would store the 224 plus pounds into the weight field of the third structure. Finally, I'd do something similar for age, and it would be stored here. Since I was talking about the third structure in the array, the index number was 2. Now that makes it real simple for high-level programmers because when you think about it, what does that 2 mean? To get to the third structure, the compiler had to take that 2 index, multiply it by the size of one pet structure, and add that to the address represented by the array name mypets. Stop and convince yourself that when you take the index 2 and multiply it by the size of one pet structure, which is 28 bytes, you get 56 for an answer. But here's the important thing. That means the third structure begins at an address that is 56 bytes beyond the start of the mypets array. As high-level programmers, we can think, oh, I just want the third structure represented by the index 2, and the compiler does all the address calculations for us. Guess who gets to do the multiplying and addition in assembly language for this? Let's take the idea from how high-level languages work with arrays of structures, and then just duplicate it. Let's go beyond what the textbook showed you and incorporate a procedure into the process. So here's the plan. We'll declare an array of 3 pet structures. In the third structure of the array, we'll store the same information that we did in the high-level example. To do that, we'll send the address of the third structure in the array to the same procedure we looked at before. The only thing different will be how to calculate that address. Here we go. Once again, I'm using a temporary string to hold the name I want to store in the name1 field. Realize that string could come from user input too. Here I'm just declaring it to show you how things work. Also, I'm using a temporary weight variable that's going to hold Beethoven's weight. It too could come from user input. Now look at my variable named index. It's acting like a high-level index would. In other words, the 2 here means index 2, which means the third structure in the array. We're going to use that index just as we would in high level. And the last declaration I make is the array named mypets. That array will contain 3 pet structures. So much for these declarations. Let's look at some code. First of all, I get the address of the mypets array into a register. Here it's the EBX, but it could be any general-purpose register. Then I use the type operator to store into the EAX register how many bytes a pet structure holds. Now we do what the compiler did for us. That is, we multiply the index times the size of a structure. We should get 56. Then we add that 56 to the address held in the EBX register, which means EBX holds the address of the third structure in the array. That's what we push as the first parameter onto the stack. Like in our previous example, we're sending one structure to the procedure in order to fill it up with data. The procedure doesn't know or care whether the structure it receives is an individual one or that it comes from an array of structures. The next 4 lines of code haven't changed. They send the necessary information to the procedure. Let's watch this in Visual Studio. As discussed earlier, I have 2 new variables in the data segment, the index variable with the value 2 and the array of pet structures that I'm naming mypets. Check out the Watch 1 window. There's an important difference to enter the array. I'm using the ampersand to indicate the address of the array, and the comma 3 says, show me 3 array elements. Then when I click on the arrow, I can see all 3 structures in the array with index numbers 0, 1, and 2. And I can click on the arrows by each one of those structures and they reveal their individual fields. So I set up the Memory 1 window, and when I do, you can see the 3 structures in the array. Once again, for debugging and illustration purposes, I set all of the characters in the Name1 field to X. That makes it easy to find my individual structures in the Memory 1 window. So I know here is structure 0, here's structure 1, and here's structure 2, and that's the one we're going to be paying attention to. On lines 23, 24, 25, and 26, I'm calculating where the third structure is located. So EBX is pointing to it here in RAM. I push that address onto the stack, followed by the other 3 parameters, just like we did before. Once again, I make the procedure call. Inside the procedure, everything works just as it did before, but notice what happens on line 47 when I copy the name Beethoven into the Name1 field of the third structure. In the Memory 1 window, we clearly see the name and the terminating 0 being stored. The first character of that name shows up in the Watch 1 window. Then we see the weight for the third structure being changed from the code on lines 49 and 50, followed by the age being stored on line 52. How could we have done this differently? Well, another choice would have been to send the whole array to a procedure along with what index to operate on. Or there could have been a loop inside a procedure to process an entire array. There are a lot of variations that we could come up with, but if you understand this short little program, you can modify its code to work in those situations too. My idea of writing the procedure this way would allow me to change just one structure, and this procedure could be called from a loop in a different part of the program. That was my thought behind it. I hope these videos have given you a better perspective on using structures in your assembly programs. One way to approach assembly is to ask yourself, how would I do this in a high-level language? Then try and translate that to assembly language. When you're totally lost about how to do something, that's a pretty good place to start. Hey, thank you for watching this one. Until next time.